Welcome back to compiler construction. After we took a short look at intermediate representations already in the previous lecture, we'll now go into more details on intermediate representations, and we'll also take a look at a special form of intermediate representation called the static single assignment form, or SSA. So in today's lecture, we'll first talk about efficient implementations of intermediate representations. Then we'll take a look at how to translate an abstract syntax tree into a linear intermediate representation form. And finally, we'll discuss the static single assignment form. So let's take a look again at 3-address code. We know that most operations in 3-address code have the form I equals j op k, so we have two input variables j and k. We have an operator combining these two, and we finally assign the result of this operation here to another variable I. So we have one operator, two operands, and one result. Some of the operators will need fewer arguments, for example, immediate loads and jumps might only require one target address. And sometimes we might need an operation with more than 3 addresses for special cases. Nevertheless, in most use cases, 3-address code is reasonably compact because most ops consist of 4 items, so an operation here, and 3 names of variables that are involved. Both the operation and the names are drawn from limited sets, so you only have a limited set of operations in your programming language or in your intermediate representation, and you have a limited set of names, for example, variable names or numerical constants. Storing an operation typically requires 1 or 2 bytes, and names are typically represented by integers or indexes into a symbol table. So whatever you use, 4 bytes is usually enough for storing each name. So essentially you can store them compactly in a data structure, and which data structure you actually choose for storing your 3-address code instructions affects the costs of doing operations on this intermediate representation. For example, if you want to perform optimizations on your intermediate representation code. So here's again an example for 3-address code. We've seen already that 3-address code resembles a RISC-like register machines instructions. So operands have to be loaded into virtual registers before they're used, and operates other than load or store operation. Those operate on values of our physical virtual registers. And again, results of an operation are delivered in registers. Compared to a real RISC machine, we have limited constraints for naming and allocating registers, so we can have arbitrary names, we can have an arbitrary number of virtual registers, whereas in a real physical machine we would be constrained by whatever number of registers, for example, our machine would allow. So for this simple arithmetical instruction here, a minus 2 times b, we might have this 3-address code here. So first we load a constant of 2, so we're following operator precedence here, into temporary register or temporary variable t1. Then we load the value of variable b into register 2. Then we perform the operation here, so we have a 3-address code operation involving 2 operands here, the virtual registers we've just loaded, an operation multiplication here, and finally we assign the result to a new temporary register t3. And finally, we want to evaluate the rest of this operation, so we need the value of variable a here. So we load variable a into yet another temporary variable 4. And then finally, we perform an operation on the intermediate result, 2 times b, which we stored in t3 here. And we subtract this value from t4, in which we just loaded our variable a. And finally, we assign this result to t5. Now, if you look at a real machine, for example, an ARM processor here, the ARM assembler code for this arithmetic instruction looks pretty similar. So first we use a move instruction to copy the immediate value, which is 2, into register 1. Then we need to copy the value of variable b into another register. Now this takes a bit more overhead because in a RISC machine you first have to load the address of that variable, so the pointer to the variable, into a register before you can dereference that pointer. So you load the contents of memory at the location we loaded in R2, which is the address of b. And since we don't need that address again, we can reuse R2 here to stay consistent with the numbering on the left-hand side. So this means that the previous contents of R2 are used as an address to dereference memory, and the memory contents at memory address in R2 are then loaded into R2. So this contents overrides the pointers. Then we can execute our multiplication here. So we multiply R1 and R2 and store the result in R3. Finally, we load the value of variable a from memory again. So we use the same approach as loading the value of variable b above. And finally, we can perform our subtraction operation here. So you see that there's a strong correspondence between our 3 address code and our ARM RISC assembler code on the right-hand side. So when you want to store linear intermediate representations like our 3 address code, you have different choices, and the choice of your representation, so of your data structure, influences how efficiently you can actually change this data structure. So on the right-hand side, we have our 3 address code example again. And now we can store this simply in an array. So for each of the 3 address code instructions here, we have a row in our array here, and this contains a structure with several entries. So we always have a target here, we have an operation like an assignment here or multiplication, and we have one argument or optionally another argument here. So for our assignments here, we only need one argument and the operation is actually an assignment, whereas for our multiplication, we have an implicit assignment here of the result of a multiplication to our target register here, and this takes 2 arguments. Now, storing it in a simple array is the most simple form. We can use a short array just to represent each basic block of our code separately, and very often the compiler writer can choose to place this array directly into nodes of our control flow graph. Now we can use some more sophisticated approach. So what we could do is we could store each of our 3 address code instructions separately in memory, and then we could allocate an array of pointers where, in increasing array order, these elements of the array just point to the respective 3 address code instruction here. So this means we only need to allocate the array here inside of a control flow graph node, but we would also need to provide storage space for each single 3 address code instruction somewhere else in memory. And finally, we can use a linked list. So these linked list links the quadruples, also our 3 address code instructions, together to form a list. So we only need to store the initial pointer in a control flow graph node representing a basic block, and then we just follow this additional field here, which just points to the next 3 address code instruction in the list until it finally reaches the end, which is usually represented as a 0 pointer here. So this only requires us to store one single pointer in our control flow graph node compared to an array of pointers or a whole array of 3 address code instructions. But we have a fixed order, so we can only access the elements of the instructions of our basic block in order by traversing our linked list here. So what do we use these representations of intermediate representation instructions for? Now, a very common use case is the optimization of code. One example for optimization is when you want to rearrange code in a block. For example, the costs involved by instruction 2 and 4 may be relatively high because they involve an access to main memory, whereas the instructions 1, 3, and 5 only are internal instructions operating on register values. This means that after we started executing instruction 2 here, we have to wait for the value of b, returned from memory and stored into T2, before we can start the instruction 3, which uses the value in T2. And the same happens as a data dependency between instruction 4 here, which loads a, and then instruction 5, which finally reuses the value of a, which we stored in T4. So what we could do to hide these latencies of memory accesses that take a long time is we could move these values to the front of our block. So we could move the instruction at line 2 to the front of our block, and we could also move the instruction at line 4 to the beginning of the block. So that means we could have intermediate instructions not accessing this data, like instruction number 1, which can come in between, so we have more time for the results of our memory loads to appear in the registers. So we see that we have 2 classes of operations, one class that only operates on registers like number 1, which uses a constant, and this is usually already contained in an instruction, so we don't do a memory load for this, or arithmetic operations like multiplication and subtraction. So these are fast, and we have slower instructions that access memory. So we load or store values from or to memory. And the question is, when we want to do this reordering in order to optimize our intermediate representation, what's the actual cost of doing this depending on the form of intermediate representation we chose? So let's just consider the one case of moving the instruction number 2 to the start of our basic block here, so the red one here. So this involves moving the contents of array element 2 for an array representation to array element 1. Now this would override array element 1 here, but we need this instruction, so before we can do this move, we have to copy out the information in our first array element to some intermediate storage location here. Then we can do the move of instruction 2 to the location of instruction 1. And finally, we can copy in our saved instruction, which was originally at location 1, to location 2. So we would essentially need to copy one line of that array here. Then we would need to move or copy that line at instruction 2 over to 1. And finally, we need another copy operation to store our saved instruction, which was originally at location 1, into location 2. Now, if we use an array of pointers for our intermediate representation, well, it gets a bit easier because we only have to exchange the pointer values. So what you have to do to exchange instruction 1 and instruction 2 is just switch the 2 pointers in our array around. So this still involves copying. We need to copy the pointer that originally pointed here into array element 1 here. And before we can do this, we need to save the pointer at array element 1. And then we can restore it into array element 2. So we essentially swapped just the 2 pointers here. So this still involves a copy, but now we only need to copy a pointer, so maybe a 4 or 8 byte value instead of a whole line of our array. And finally, for a linked list, it gets a bit more complicated because in a linked list, we have to indicate the start of an array. So our array or list now no longer starts at instruction number 1, but instruction number 2. So we have to change the start pointer to pointer instruction number 2. But this means we have to store the initial pointer to the start here. And then we also have to manipulate the following pointers here, because after our element 2, now we need to switch this pointer to pointer element number 1, the one we stored before. And finally, the pointer in element number 1 now has to point to element number 3 in order to ensure the right sequence of instructions in our reordered linked list here. So we finally have the pointer pointing here. Then we need to reroute this pointer to instruction 1. And finally, the pointer in instruction 1 to pointer instruction 3. So we have to save 3 pointers here instead of 1, and we have to restore them accordingly. So that's a bit more of overhead. So now let's take a closer look at 3 address code. So most modern computers still try to maintain the illusion that they are a von Neumann machine, even though they are far more complex internally. So this means a von Neumann machine has 3 main components: a control unit controlling the execution, a data path, and arithmetic logical unit doing the calculations in a machine and the data movements. And finally, an important characteristic of a von Neumann machine is that it has a unified memory for instructions and data. And the instruction execution in a von Neumann machine is executed by a clock. So this clock might, for example, split an instruction into 4 phases. You've seen this when you already looked at CPU pipelining or similar. So we can split an instruction into instruction fetch from memory. So this memory is addressed by the program counter. So this instruction is passed, so the program counter is passed from the control unit to our memory, and the memory returns the instruction at the memory location our program counter points to. We can do an operand fetch. So this operand fetch takes place in the data path here. So the data path can generate an operand address to main memory, and the main memory can return this data to be processed on. As a third step in an extraction execution, we can then finally execute the instruction, and then we would write back the results from the data path either into a register in the CPU or maybe into memory. So from this splitting of the instruction execution into different phases, we actually need according instructions in our intermediate representation. So we need instructions for the control unit, we need data for our data unit in ALU, and we know instructions and data are both located in memory. And since we don't want to deal with hexadecimal addresses of memory locations, we can make our life a bit easier when specifying an intermediate representation by using symbolic names for addresses of instructions and addresses of data in memory instead of these numeric addresses. So for instructions, if we need to refer to the address of an instruction, for example, as a target of a branch instruction, we call these symbolic names labels here, whereas for variables, they're just variable names. And accordingly, we can categorize our instructions in our intermediate representation now. So we have mathematical, logic, and data movement instructions here, like binary and unary operations, copy operations, and load store operations. So these are mostly concerned with operations in the data path. And we have control flow operations like conditional, unconditional jumps, and maybe procedure calls in our intermediate representation. So our 3-address code is actually a form of a low-level intermediate representation, and we've seen that we deal with at most 3 addresses in memory plus the instruction ourselves. And so we can have different forms in our simple example intermediate representation. So binary operations have the form we've seen already. So we have 2 input operands, B and C. We have a binary operation combining them like an addition or multiplication, and we assign the result to a third name here. A unary operation only has a single operand for its operation, like a negation, a binary negation, which would just flip bits around, or a numerical minus, which would just give the negative value of the operand, and of course a target again. We can have a copy operation here, which just assigns the value of B to another name, A. And then we can finally have load and store operations, so we can take the address of a name here, like the C operator that you already know, the AND operator here, and assign it to a name. Or we can have a dereference of a pointer, so if we have an address stored in name Y, we could use this to dereference the memory location here, so get the contents of the memory location, store them somewhere. And we have a simplified version to access arrays, so we have a base address X with an offset in the array I, and we can assign a value to that also. So those were instructions for handling data, and control flow is equally simple to express in 3-address code. So we've said that we want to have names for certain instructions here, so it's especially for branch and jump targets, and these names are called labels. So labels are just a name followed by a colon, and usually this name starts at the very left side of your line, so usually at the beginning of a line. So label L colon means that the next address, the next instruction following the address of this instruction is also given the symbolic name L. And when you now want to change control flow, you can, for example, do an unconditional jump. So you jump to a label L, which means you jump to the instruction following that label L in your intermediate representation code. You can also have conditional jumps, so you can check a condition X, and if this condition is true, then you just jump to location L. You can switch it around, so if a certain condition is actually false, this is if false, you can go to L. And we can have several comparison operators, like if X is less than Y, if X is greater or equal than Y, and if X is not equal to Y. We can also conditionally jump, and always when we have a conditional jump, only when this condition here is fulfilled, then we take the jump. If not, we just fall through to the next instruction that comes after our conditional jump. And finally, we can have calls and returns, specifying parameters here. So we can say X is a parameter for a function call. Then we can call a label L. So this means a call jumps to our code at location L. And it also remembers where to return to, and whenever we execute return instruction, this remembered call location is then used to continue execution after your call instruction. So how can we translate a given intermediate representation as an abstract syntax tree to our linear 3-address code? Now, first, let's take a look at how we translate binary operators. Now here we make use of the nature of the abstract syntax tree, that it's a recursively defined data structure. So no matter how complex the contents of an expression combining E1 and E2 are, this can always be translated into a simpler form. So if we have some expression that says we want to assign the result of a translation, that's what the capital T stands for, and what we translate is here in square brackets. So we want to translate the expression E1 operand E2 and store the result into 2. We can always break this down into translating expression 1 first, storing this intermediate result into an intermediate variable T1. Then we translate our expression on the right-hand side, E2 here, store that intermediate result in another temporary variable T2, and finally we can take the results of these two temporary variables here, so the results of actually translating our two partial expressions here, can combine them using the operator that was specified here, and finally store the result in another temporary variable T3 to combine the two basic results. So that means when we have an operand here, and this maybe combines larger subtrees here for more complex expressions here, we can recursively go down until we hit the leaves of the tree to then construct our partial expressions and go up and up again until we can construct this operand here using the temporary results from evaluating the left and the right hand side of our node here. So this is called linearizing our program, and we do this by traversing the abstract syntax tree in depth first order. So we start with our multiplication operation and then go depth first, and so finally we find an expression which has two numbers here as the leaves. So we can translate this. So we can translate this node 1 here, which just gives us the idea that we have a constant 1, into loading the constant 1 into the first temporary variable. Then we load our constant 3 into our second temporary variable. And finally, we combine both using the operation indicated here. So we say T1, T2, we combine them using plus and store them in yet another temporary variable, which we call T3. And then we can continue further up the tree. So we know the result of our plus operation is stored in T3. So we can use this as the left-hand side expression for our multiplication. So we do another depth first order traversal and end up at our 5 here, which is a leaf node. So we know we can copy the value of our left expression, which we stored in T3, into a new temporary variable T4. We can copy the immediate value 5 into register T5. And finally, we can combine the two new intermediate results in T4 and T5 with a multiplication operation and store the result in T6. And then finally, we could copy the final result of our multiplication out into some receiving variable T. So if we have nested expressions like this, we just combine the local parts in our translation process recursively that represent a subtree. So we start with our very simple operations here as a translation of 1 plus 3 and a translation of T3 times 5 here. And then we can combine this again and finally combine the total result in the assignment here to our final representation of our translation. So essentially we would start from the top and then translate the parts of these recursively down to our required 3-address code implementations for our simple expressions that involve the leaves of our node or some intermediate results we already obtained in a previous deeper traversal on that part of the tree we were considering. What else do we need to translate? Now, statement sequences, so just having one statement after the other, they are straightforward, so they are already in sequence. So if we want to translate a statement sequence as 1, then as 2, then as 3, and so on, into 3-address code, we just write the translation of these three sequences of statements one after the other. So we simply translate one statement after the other and append their translations in the order they occur in the original representation. For assignments, we need to copy a value. So an assignment looks like this in our abstract syntax tree. So we have a target here and we have an expression, and the value of this expression should be assigned to this target. So this requires copying a value. So if we want to translate the expression v equals e, this requires us to take the result of e first. So we have to translate our expression here on the right hand side, because this can again be a subtree of a complex expression here. We have to assign the result to a temporary variable, and finally we copy this temporary variable over into our receiving variable v on the left hand side. We can also assign values of expressions to arrays here. So for this we need to calculate the index or address offset inside of the array, and this itself could be an expression here. So for example, we want to assign the result of evaluating the expression e2 to an array element e1 of our array v. So we have a name here on the left hand side, and then we can have an expression here calculating an index number for our array here. So we need to evaluate two expressions. First, the index expression to know in which element of v, so at which offset of our memory address of v, we need to store the result. And of course, we need to calculate the result e2 here, and finally do a copy operation. So to translate this array assignment into 3 address code, we would first need to translate the expression giving the array index, store this one into the first temporary variable, then evaluate the expression we want to assign, e2, store this into our second temporary variable, and then we can finally use a 3 address operation, just assigning this temporary variable here into our array at offset e1. So let's now consider control flow. So we have some expressions we want to translate, like an if expression here. So if a certain expression is true, then execute some statement sequence S. So this requires control flow, so we need conditional jumps here. This would be our S node here. So if, and this if node has a condition here that needs to be evaluated, and a statement or sequence of statement that can be executed conditionally. So we first need to translate our expression again, because this again can be a more complex expression, store its value into T1, and then we need to turn the condition around, because if a condition is fulfilled, we jump. So only if our condition was not true, so if it's false, then we change our control flow and jump over the next part to our label end. And this label end just indicates that whatever is generated after this label is the target of our jump. So we would jump to the instruction that comes after lend, and this results from the translation of the next statement after our complete if statement here. And only if T1 was true, so if T1 was not false, we just fall through here, and then we need to consider this statement S, and this can be a statement sequence, so we would need to translate whatever S is into intermediate representation recursively first, because we could go deeper in our tree here. So if E is true, our expression here, our control flows through our instruction S, whereas if E is false, we skip the complete translation of S and continue at the first instruction after the translation of S. So that's why we introduce this label lend here into our code. Of course, we can also have more complex conditionals, so we can have an if-then-else construct here. So this is represented like this in an abstract syntax tree. We still have an expression here, and then we have a statement sequence 1 representing the then part, and we have a statement sequence 2 representing the else part, so that's taken when the condition is not fulfilled. So the first part is similar, so we first evaluate our expression here, and if this expression is not true, we skip over the translation of our then part of our if statement here. Now then, we also need to find a place for storing the else part here. So we skip to a label else and translate the else instruction here. Now we have to ensure that when all of our translated statements for the then part have finished, we don't accidentally fall through the else part. So we need to jump over the else part now, like we've just jumped over the then part. And again, we jump over the then part if the other part of our then of our if instruction is required. And finally, our control flows converge. Either if it was true, our condition was true, so we jump to the end here, or if it was false, we just fall through the end here, and our control flow converges at our first intermediate representation instruction after our label end. Now, if we consider loops, then we have to deconstruct the loop because we don't have any loop constructs in our intermediate representation. So we deconstruct our loop by changing it into a condition check, a conditional jump, and then we execute the body of the loop if this condition was fulfilled, and then we jump back to the start of our loop. So this is our AST representation here. So while an expression is true, we execute our loop body S here, which may consist of one or more instructions, or even 0 if you wanted. So translation of while expression do S becomes that one here. So we need to add a label to the start here because we always test the expression from scratch when we enter our next loop iteration. So before we enter our loop, we first test our expression. This means we have to evaluate our expression first, assign the result to a temporary variable, and if this expression's result is not true, so if it's false, we jump over the body of our loop. So we again add a label end here. If our condition was true, we then need to add a translation of our loop body here to our intermediate representation, and then we need to start the loop again to check the condition again for our next loop iteration. So we need to do an unconditional branch here, which is called a jump in our intermediate representation, to our label at the start, test, to enable our intermediate representation code to re-evaluate this expression. This might have changed because of code inside of the loop body, and then check again if this loop condition is still fulfilled, enter the loop again, or if it's no longer true, and then leave our loop body and jump over behind the end of our loop. Of course, you also know other sorts of loops, so like for and repeat loops. Now these can be easily transformed into while loops, so you don't have to provide a special translation for them. So for example, a for loop running from 0 to 9, incrementing I by 1 every time doing something, can be translated into a while loop that initially just initializes our loop variable I, then checks for the condition if I is still less than 10, then it does something, and we need to do this increment of our loop variable as the last instruction in our while loop, and then it starts again. Similar is our do loop. So our do loop differs from our while loop by always first executing one instruction, one iteration of the loop body before checking for the condition here. So if we have a do loop here, we execute this while this condition is true. So we can translate this into do something, and then while this condition is true after the first iteration of our loop, we can do something again until this condition is no longer true. So another control structure is our switch statement here. So our switch statement is essentially a shorthand for writing a set of if statement to check for certain values in an expression here. So if we want to translate a switch statement that evaluates an expression here, and depending on the value of the expression, if it's value 1, executes block 1, if it's value 2, executes block 2. We have this rather complex intermediate representation as an AST here, and this can of course go further to the right if we have more cases in our switch statement here. We have to evaluate our expression first, translate the evaluation of our expression, and store the result in T. Then, well, if our value is not v1, which would consider the first case here, we skip over it. Otherwise, we translate our first statement sequence here for value 1. Then we check for value 2. If this is not the case, we jump over here. Otherwise, we translate, and so on until we reach the last one, which would skip over to code after our switch statement if the condition was also not fulfilled. Now this has a bit of a disadvantage because you see the more cases you get here in your switch statement, the longer your chain of if statements get. So you always have to check all the conditions here again, so the values here again, and jump over them until you hit the end. So this takes a lot of time, especially if your switch statement has a large number of cases. So we can also employ a better way to do this. So this better way to implement a switch statement is using a jump table. So what this does is, again, it evaluates our expression e here, stores this result into our temporary variable t, and then we just jump to a jump table location indexed by the result of our expression e. So we index our table to jump to by our result t, and then we have the names of labels in our table. So we just have label v1, label v2, label vn, and finally we can have a label end if none of these were true. And then again, for each of these possible values here, we need to translate the related statement sequence here. Now what you see here is that we don't add a jump to end here at the end of our translation sequence. And this means we model the behavior of C code. So when you have a switch statement in C and you have a case, then you automatically fall through to the next case unless you write a break statement at the end of this specific case. So when you translate it like this, you actually get a translation of the C behavior. And if you don't want this, you would need to add the jump end after the translation of each of the statement blocks here for each of our cases. So in addition to providing this translation here, now we need this jump table here as a data structure. So this has to be provided as part of the intermediate representation, which then maps the numerical values for our conditions v1, v2, which were stored in t as a result of our evaluation, and maps these numerical values to these respective labels lv1, lv2, and so on. Now, one problem that shows up when we are considering intermediate representation generation is that we generate a large number of labels. And the problem is when we want to analyze and translate this intermediate representation later on, we need to ensure that these labels must be unique. Now, this can be easily handled by just numbering the statements that generate the labels here. So, for example, if we have two if statements here, if expression 1, then sequence 1, if expression 2, then sequence 2, then we just start numbering them. So essentially we would use L and 1 for our first if here, and then we have our second instruction, which would just use L and 2 to generate the label, and of course also generate our target for our conditional branch instruction here. Now you need to take a bit of care when you translate nested statements. So if you have a statement like this, if expression 1, then, if expression 2, then assign B to A. This requires a bit of care when generating the labels and the order. So you have to do this recursion again. So first you have to evaluate E1 and implement the if. Now you have to jump to end, but you cannot generate it directly because you need to recurse and generate code for this additional if instruction here. So you have an inner if here, evaluating expression 2 and checking that one. And finally, you have your statement here. So you have to recursively add the inner end label first, and then add the outer end label to ensure the correct execution order, no matter which path you take through your nested if statements here. Now, one thing we've seen in our discussion of intermediate representations so far is that we have these arbitrary temporary variable names t1, t2, and so on. Essentially, what we want to do with our intermediate representation code is we want to analyze the data flow through our program. And for this, it is very useful to actually keep the names of the variables we're using, but on the other hand, also be able to identify if this value has been overwritten somewhere. And this is exactly what static single assignment form helps us with. So static single assignment, or SSA, is a convention for naming intermediate values here, which is used in almost all modern compilers to encode both information about the control flow and the data flow in your program. So names in this static single assignment form now are created to uniquely correspond to specific definition points in the code. So whenever we create a value here, so we assign something, we need to create a new name, but we need to also, or we want to also keep track of which variable this was originally assigned to. So each name is defined by one operation, and this operation is an assignment operation. So this is why it's called static single assignment here. Static single assignment abstracts from our virtual processor registers, so it's a bit of a higher level representation because it helps us to name intermediate values for variables during the compilation and computation process. So if we have a name x for a variable, then each use of that name of an argument in some operation encodes information about where the value of this variable originated, because we no longer have just a name x, which can be overwritten multiple times, but for each overwriting we increase the index, so we can have x1, x2, x3, and if we know that a value x3 is referenced, we can check where this x3 was actually assigned, so we can know where a certain data value actually comes from in our intermediate representation. So this means that each textual name here in our static single assignment form refers to a specific definition point somewhere in a different place in our code. So we define a program to be an SSA form when it meets the following two constraints. So first, each definition of a variable has a distinct name. And second, each use of a variable refers to one of these single definitions. And if we want to transform an ordinary intermediate representation program to static single assignment form, then we need to consider the convergence of control passes. So for example, if we have an if-then-else instruction and both the then and the else part assign a value to variable x, then after converging the control passes, again after the if statement, we need to consider if the value of x came from the then or from the else part. And to do this, we insert so-called phi functions here at the points where different control flow passes merge, and then we use this phi function to rename variables to make this single assignment property still valid at this conversion of control flows. So for example, we have some intermediate representation here. We assign a value of x for x and y before a while loop. And inside the while loop, we also reassign x and y. So when we start this while loop, before the first iteration, our values of x and y would be the ones assigned up here. Whereas for subsequent iterations of our while loop, the values we have to consider are the ones we actually assigned inside of the body of our while loop. So our intermediate representation would look like this. So we first assign x0 and y0. So these are the first instances of our variables x and y. Then we have to check x0 if it is larger or equal than 100. Well, if it's so, we jump over the body of our loop here. Then we assign x1 to either x0, which comes from up here, or x2, which was assigned down here. We also assign y1 to either the value of y up here or the value of y calculated down here. So we have a new assignment to x and y, so we need to increase the indexes here to 1 from 0. And finally, we implement the two instructions inside of a loop body, so we add 1 to x. So this is the value that was either coming from up or from our previous loop iteration here. So it's x1 plus 1. We have a new assignment, assign this x2. Same for y. And then we check our value of x0. If it is less than 100, we still iterate our next loop iteration. Otherwise, we fall through. And then we need to consider the original value of x0 or the value of x2, and the same for y to assign them finally to the values for x and y after the end of our loop. So let's take a look at a complete example of translating source code into static single assignment form. We have an example here which includes some variable assignments, a while loop, and an if-then-else condition here, and finally we return the value of variable j here. So the first thing we do is we split our source code into basic blocks. So remember, basic blocks are linear sequences of code where we can only enter this sequence at the beginning and only end it and only leave it at the end using usually a jump instruction, but we could also fall through because the next instruction after our basic block would just be a target of a branch. So our first instructions are just 3 assignments. So we have our first basic block here. And then we know we have to translate our while loop into an if condition because we can't represent while loops in our intermediate representation. So we check for our loop condition here. So if k is less than 100, if this is no longer true, we skip our whole loop body and just execute return j. So this is our false part. So we know we jump after the if. So this if is a basic block on itself. This return is the branch target and is our last instruction here. So it is also a basic block on itself. Now, if our condition is true, we need to translate our loop body here. So our loop body consists of an if statement here. So this if statement either jumps to the then block here if the condition is fulfilled, or jumps to the else block if the condition is no longer true. And so it means our next basic block actually starts and ends at this if instruction already here. And then we have these 2 assignments here as a separate basic block here, and these 2 assignments here on the in the else block as our next basic block here. Finally, our control flows converge into, now we have this empty basic block B7. We'll see in a bit where we've introduced this. And finally, from B7, we return to the start of our loop to check for our condition once more. So this is the first part of our translation, and this is a control flow graph that represents the control flow in our program, but this no longer, not yet uses an SSA representation. So let's first introduce unique identifiers using a naive approach by just using unique static variable assignments here. So we have no longer I, j, k, but we have I1, j1, k1. So we check for k1 is less than 100. Then we have the first check of j here, which is j1. And then we assign this. For example, here we use just the number of the basic blocks for an assignment to make it easier to get unique names. So here we would assign j5 and k5 because we're in basic block 5. And on the right hand side, we would assign j6 and k6 because we're in basic block 6. And finally, we converge. And then we have a problem, as you can see. So the problem we have here is when going back to the next loop iteration, because we translated our code naively, so we just used unique identifiers for the assignments and then used the first unique identifier we saw, so k1. So what happens when we run through this loop once? Now the value of k got updated here, either in the then or in the else part here. So the current value that is relevant for k is either contained in k5 or in k6. So after one iteration through the loop, k1 would be incorrect up here. So we have to decide which k is the right one. Is it k1 from up here? Or is it maybe k5 from here? Or k6 from the right-hand side? And of course the answer, it depends. And this depends upon where the control flow was coming from. So if we enter our while loop for the first time, of course, our variables came from up here. Whereas when we leave our loop body, our variables came from either left or the right. Now we've seen our phi condition usually only combine 2 variable values, and we have 2 convergences of control flow. So first, our control flow converges again after our if statement, so either after we're executing the then or the else part here. And after this convergence, then we jump back to the start of our loop. So that's why we introduced our empty basic block 7 here before, in order to be able to converge the values here. So what we do here is now, first, we need to converge the values from the left and right side here. So we need to use a phi function that chooses either j5 if we were executing that pass here, or j6 if we were executing this pass here. And then the result of this is the right one, either the left or the right one here. And we assign the correct one to a new instance of j, which we call j7. And we do the same for k, so we have k7. So we know that the current value after executing one loop body for k is always contained in k7. So we can jump up here again. And now we know that the value of k either comes from up here, so it's k1, or it comes from down here, so it's K7, and we can do the same for the value of J, so J2 is either J1 from up here or J7 coming from down there. And now we can add this new name here, K2, as the value to check the condition for. So if this new K2 here now, which can either be the value of K1 or the value of K7, depending on where we came from, if this one's less than 100, then we would essentially enter the loop, and otherwise we would just skip over the loop. And then we could return our current value of J, which is now J2. So we introduce a selector function in all places where control flows converge. So either we converge down here after our if statement, or we converge at the start of our loop because we can come from instructions before the loop, or we can come out of our loop back again to the start. And the selector function then copies the correct value of the variable that was indicated to a new intermediate variable, and this depends on the knowledge of the compiler about our control flow. And so here, using this phi function and the unique naming of variables wherever it's required, we now have transformed our naive control flow graph to a control flow graph that correctly uses a static single assignment form. So the question remains, when we do this transformation, where do we need to place phi functions here? Of course, phi functions are copies, so copies are costly, so we want to avoid copies wherever we can. And the minimal number and placement of these phi functions is a bit more complex than shown in this simple example. So in general, we would want to generate a minimal SSA, and this can be done using dominance frontiers, so a technique to determine the basic block defining the current value of a variable. If you're interested in details on this, there's a literature reference for this included at the end of the slide set. So we won't go into details on minimal SSA construction here and the placement of the phi functions. So if you're interested, here's a reference from 2001 defining an algorithm for this, and we have additional references to SSA and the relation to functional programming, which is quite interesting, and also how to efficiently compute static single assignment form from the control dependence graph. So you see, these references are a bit more recent than the 1960s and 1970s references we've seen. So in terms of compilers, SSA is a relatively recent invention, though it's almost 30 years old now. Still, if you find some older books on compiler construction, they're not very detailed or don't include discussions of SSA at all. So, for example, if you have a first edition of the classic Dragon book, that doesn't actually have a discussion of SSA because it was written before SSA was common. So what's next in our compilers course? Well, we've seen translation of control flows, loops, if conditions, and linear statements of statement sequences. So now we have to look at functions and procedures. So in our next lecture, we'll take a look at the abstraction of procedures, how to use and how to translate them. That's all for today. Thanks for listening, and until next time, bye.